Packed house. Thank you for joining me. What I hope to accomplish in this talk is to give you an appreciation of TLS 1.3. And we're going to do that by examining the security improvements that it gives over previous versions of TLS and kind of the performance enhancing things that it introduces. Then we're going to also discuss secure deployment of TLS 1.3 and some things that you might have to consider when you're doing so. So first, the boring stuff. I'm Alex Balducci. I work at NTC Group. We're a giant security consulting firm. We do pen testing, hardware hacking, network penetration tests, all across the board. We also have groups that do compliance, PCI, ISO sorts of things. So, we're really involved in the whole security world. I myself am part of our crypto services group, where I focus mainly on crypto things. So recently, I've been reviewing a lot of blockchain implementations, smart contracts, secure messaging applications. But we really run the gambit of different things that we look at. So we've done high-level protocol reviews and low-level implementation details of cryptographic primitives. Who here has heard of CryptoPals? Have you done CryptoPals? So this is how I learned crypto in the first place. And it's these really fun sets of challenges.
Awesome. Totally
Thank you.
You will have your mind blown about how simple it comes down to the next part.
Exactly. It's not all this crazy math. It's more like logic puzzles. And they're a lot of fun. So I implore you to do them. Like I said, that's how I really got my interest and knowledge of crypto. My email is here. Do the problems. Ask me questions. It's never annoying. I'm always happy to answer. Okay, so on the TLS. So I like to start by discussing the security properties that we want in a secure transport protocol. And I'm going to do this from like literally a high level, but it will give us a good base of the rest of the discussion. So first, we want confidentiality. So I'm the client, you're the server. We should be the only people who can read the messages. So we have to somehow encrypt our messages. So we need some shared secret between me and the server. So we're going to have to do a key exchange. Now, we're going to dig into the handshake later and talk about what that key exchange looks like, but note that we have to do that. And once we have those keys, we can use them to derive more keys to encrypt application data between the client and the server. Next, we want authenticity. I need to know who I'm talking to. If I'm a user and I'm trying to visit bank.com, I need to be sure that it's bank.com and not actually some attacker-controlled domain. And you probably know how we accomplish this. So we have the certificate authorities. They're going to verify that bank actually owns bank.com and issue them a certificate. So then when I'm the client, I visit bank.com, and they provide me with their certificate. I can check the signature against the CA's public key. The CA's public key lives in my browser or in my operating system, and therefore we can achieve authenticity, right? We also want integrity. We need to make sure that an attacker cannot modify any of the data that we send back and forth. So there's two ways that we can do this. We could have an HMAC. So we might encrypt our data and then apply an HMAC after that to provide integrity. So then when the server receives my message, they can perform the same HMAC, check the tokens, and then see if it's been modified or not. We also have these new AAD modes that encrypt while providing integrity. So it's just one operation, you get confidentiality and integrity at the same time. Kind of cool. And we also want forward secrecy. So if the server's key is compromised at this point in time, my previous sessions with that server should not be compromised. Okay, so those are the security properties that we want. Now we're going to go on a journey that the working group performed when they started drafting TLS 1.3. And they looked at previous versions of TLS and said, where did these properties fail and why? How do we fix it? So one of the big sources of failure are the cipher suite choices. There's 229 cipher suite choices defined in all previous versions of TLS. I tried to make this a dramatic slide and have like a typewriter effect and explosions, but it crashed Keynote when I did that. Okay, so not all of these are great choices. TLS 1.2 itself defines 37 of these, with a few added ones. But we have to ask ourselves, are all these cipher suites, the same strength? Well, let's take a look. So this first one, we're performing TLS with RSA as a key exchange. How does the RSA key exchange work? Well, I, as the client, I generate this master secret. The master secret's going to be what we use to encrypt the application data back and forth. In RSA key exchange, I have the server's RSA public key. I encrypt that master secret to that and send it to the server. Okay, but does this have forward secrecy? So my first session, I generate a secret, encrypt it to the RSA public key, give it to the server. Next session, a new secret, but encrypt it to the same RSA public key, and so on and so on. So if an attacker reveals the private key corresponding to that RSA public key, they can decrypt those past sessions. So I don't like that. Okay, so TLS, RSA as a key exchange with RC4 as the encryption algorithm. Well, what's RC4? It's a stream cipher. How does it work? We key it with that master secret, and we ask it to spit out bytes. It's basically a random number generator. So it's going to spit out these bytes that we're going to call the key stream. And we XOR that with our plaintext, and we get our ciphertext back out. That's how a stream cipher works. The problem is, it's been shown that RC4 has these biases in the key stream. So for instance, the first byte that comes out of your RC4 key stream has a I think it's a half chance of being a null byte. You'd expect that to be a 1 over 256 chance, right? So that's a pretty huge bias. So an attacker could use those biases to their advantage and glean information about the plaintext, breaking our confidentiality security assumption that we want. So I don't like RC4. And finally, we know that MD5 is vulnerable to hash collisions, but it's also vulnerable to these sloth attacks in the TLS context that provide an avenue for an attacker to perhaps impersonate a server, breaking authenticity. So I don't like this cipher suite. The next one, TLS using Diffie-Hellman as a key exchange. Well, how does Diffie-Hellman work? In each session, both the client and server are going to generate a Diffie-Hellman private key and public key. Now, if I, as the client, supply the server with my public key, the server gives me their public key, we can do the Diffie-Hellman operation and agree on a shared secret. That's awesome. But in this case, it's Diffie-Hellman anonymous. That means the server is not providing any authenticity of the Diffie-Hellman public key it gives to the client, which opens up the avenue of the basic Diffie-Hellman man-in-the-middle attack. An attacker could substitute the server's public key with their own and man-in-the-middle connection. I think that's set 5, problem 1, if you want to investigate how that actually works. So I don't like that. Okay, our cipher suite choice is AES 128, perfect, but it's operating in CBC mode. Now, CBC mode is a perfectly fine mode to use if you're using it correctly, which previous versions of TLS did not, giving rise to the Beast attack or Lucky 13. So I don't particularly like that. And then SHA-256 as our hash function, more or less, it's the same choice. But overall, that's a pretty poor choice of cipher suite. This last one, we're using Diffie-Hellman. And this time, the server's contribution, the server's public key, is signed with RSA. Okay, no authenticity failures here. We're using AES in GCM mode. GCM is one of these cool AAD modes that encrypts and supplies integrity at the same time. Great. SHA-256 as the hash function. Okay, seems reasonable. But we have to look at GCM mode. So GCM mode is basically CTR mode, counter mode, with some authentication magic. This counter mode is similar to how RC4 works. So you key a yes with your shared secret, and then you encrypt a nonce, a number you just use once. From that, you get your key stream, which you XOR with your plaintext, giving you the ciphertext. Now, if my plaintext is, this long, I encrypt the nonce, I encrypt the nonce plus 1, I encrypt the nonce plus 2, so on and so on and so on, until I have enough key stream to XOR with my whole plaintext. Okay? But what happens in CTR mode if we repeat a nonce? Well, I have, you encrypt the nonce, I get the key stream, XOR with my first plaintext, get my first ciphertext. When I want to encrypt another piece of plaintext, I have the same key stream XORed with a different plaintext, giving me a different ciphertext. But the key streams in both cases are the same, giving rise to this little equation that we can, maybe glean some information on. So since the key streams are the same, I have the two plaintexts XORed together equals the two ciphertexts XORed together. Now, the ciphertext is presumably public, and if an attacker knows any parts of plaintext 1, they can figure out information about plaintext 2, a loss of confidentiality. So we don't like repeating nonces. But in GCM mode, it's worse. So since it's basically CTR mode, we have the same relation, loss of confidentiality, but it also leaks the authentication key, which that goes into the authentication magic, which gives you integrity. So you've lost integrity. This gives rise to, I think, the best demo that I've seen presented at Black Hat. A former colleague, some MI5 website had an issue where they were using GCM and they were repeating nonces. So he was able to modify that server's response and inject his slides into MI5's website. Yeah. And the issue here really is do we actually repeat nonces? Well, in previous versions of TLS 1.2, they recommended you did a certain operation where you wouldn't repeat a nonce, but it was really up to the implementation itself to decide what it wants to do. And some of them said, oh, we're just going to use random nonces, and they turned out to be not so random, leading to this issue. So one big win of TLS 1.3 is they use explicitly derived nonces. It's this fixed nonce XORed with the sequence number. The sequence number just being how many TLS messages have we sent back and forth. So we don't run into any of these issues that affect GCM. So that's one nice win. So I harped on the cipher suites a lot, and there's a lot of bad ones. How many cipher suites do we think that TLS 1.3 provides or has in its specification? 37? 5. 5 sane choices. So 4 of them are using AES in GCM or CCM mode. They're both AAD modes. And then we have this Cha-Cha 21 using Poly 1305 as the authentication magic. This is great. We're using sane, secure ciphers. There's no more triple DES. There's no more DES. There's no Ghost or whatever the other ones are. They're all AAD modes, providing integrity and encryption. So we don't have to worry about encrypting and then macking or macking and encrypting or those complicated schemes. AES is great. We have hardware support for it. It's blazingly fast. And if we don't, we have Cha-Cha 20, which was designed to be fast in software. So that's just one huge improvement compared to previous versions of TLS. So I'm going to kind of sum up some of these main things in this chart. So in our previous versions, we had weak ciphers. Yeah. Your question was the Yeah, so the question is GCM a liability with repeated nonces in this case? No, because we have them explicitly defined. You have to do this. If you don't do this, you will not be able to talk to a client or a server who's implementing TLS by the specification. So summing up, we had these weak ciphers, these weak modes, these weak hashes that led to a variety of attacks. They're cool attacks, but they're attacks. Beast, Poodle, Lucky 13, Sloth, Sweet 32, RC4, no more. And we've fixed all of those by basically removing all that crap. We have 5 sane choices now. AAD modes, sane ciphers, limited choice. It's great. One question, though, is where are the key exchange modes? Before, we labeled them as TLS, key exchange mode, cipher suite, hash. Now it's just the encryption algorithm, AAD, hash. Well, again, what key exchange modes do we see were used before? We have RSA. We don't like it for lack of forward secrecy. Anonymous Diffie-Hellman, no authenticity. So we're removing that. They're insecure. We're left with Diffie-Hellman and elliptic curve Diffie-Hellman. Again, are key exchange modes that are forward secrecy or provide forward secrecy all of the time. What will become important later is there's a particular elliptic curve, NIST P256, that most implementations will probably support. So keep that in mind. So there was some improvements security-wise that TLS 1.3 provides compared to past versions. Now I want to get into some performance-enhancing improvements that it does. And to do so, I want to start with the TLS 1.2 handshake. So we're going to be doing a Diffie-Hellman handshake. And on the right side, I'm going to discuss the key schedule, what things are encrypted and what keys they're encrypted with. In the left side, I'm going to have the messages that the client and server send back and forth together. So this is the handshaking phase that's bootstrapping the rest of our session. The idea is to authenticate the server and create a shared secret so we can encrypt application data. So in TLS 1.2, the client says, hello, these are the cipher suites that I support. The server is going to pick a particular cipher suite. In this case, I've chosen Diffie-Hellman. So the server responds with, hello, its server certificate, a signature over its Diffie-Hellman public key, and the Diffie-Hellman public key. Now, the client is going to receive this. It's going to check the signature on the server certificate against its CA, providing authenticity. It's going to check the signature over the Diffie-Hellman public key, so we don't have man-in-the-middle attacks. And then it's going to respond with its own Diffie-Hellman public key. And note that at this point, the client knows all the information it needs to create the shared secret. It has the server's public key, and of course, it knows its own private key. Okay, so now it can send a finished message, but it's green. It's encrypted with the derived key. Now the server knows the client's public portion. It can create the shared secret, the same shared secret, send its own finished message. And at this point, both the client and server are convinced that they both know the same key because these finished messages are presumably well formed. And now we can send application data back and forth. So this first half, before the client sends its Diffie-Hellman public key, is not encrypted. We don't have enough information to create that shared secret. Then the second half is encrypted with the master key, the shared key, whatever you want to call it. So this design makes sense, but how can we improve on it? How many round trips do we do here? 2. What's better than 2? 1. So in comes the TLS 1.3 handshake. So here the client says hello, and it guesses what cipher suite, what key exchange mechanism the server supports. So it's going to say hello, and right then send its Diffie-Hellman public key. Now, what I said earlier is most servers and clients are going to implement NIST P256 elliptic curve, so you can probably guess correctly most of the time. Assuming the server supports that, it's going to say hello and send its own Diffie-Hellman public key. But now the server knows all the information it needs to know to create the shared secret. So it will still send the server certificate, still send the signature over its public key, still send the finish message, but they're now all encrypted. So up to that point, no encryption, no information. Now these are encrypted with a handshake key, this key derived from the shared secret. After receiving this, the client can send its own finish message. So now both parties know that they both know the shared secret, and we can start sending application data. And now we make a distinction between these two phases. So we derive another key that's going to encrypt the application data. This is cool. We've reduced one round trip. And this is important because there's a lot of, I take it for granted that I have extremely fast internet, but the people in the world who don't. And the latency of having to do 2 round trips is, it's pretty insane. And everybody deserves the right to have a secure internet experience. So this is a huge improvement. I also see like a lot of corporations that, of course it depends on what the threat model is, but they're not encrypting internal traffic because, again, the latency is slow. And maybe now, we have more of a reason for them to do that because we've reduced that latency. Okay, that's a pretty nice solution. But what's better than 1 round trip? 0 round trip. So this is a feature that the draft writers wanted since the beginning. So we're going to talk about how they achieved that. But this is also where some of the pain points come in, and a place where you need to be careful if you are deploying TLS 1.3 as a server or as a client. So to get to 0 round trip, we have to go over 2 things. First, the key schedule. Second, resumption, and then we're there. So the key schedule. Keep in mind that both parties, the client and the server, are performing the exact same calculations. They have to agree on the exact same keys to actually encrypt and decrypt the data. But, it gets confusing. So keep in mind that both parties are always doing this operation. So if we're resuming a session, which we don't know about yet, we start with a resumption key. Otherwise, we start with this string of null bytes. And we send it through this key derivation function, which we can just think of as a hash. And we get a 0 round trip key. Okay, we don't know about that yet, but keep in mind where it comes in the key schedule itself. So then we complete our handshake, and we're left with a shared secret, a shared key. So we take that and send it through the KDF, along with the output from above. So 2 inputs, and we get the handshake key. Recall that this was used to encrypt the server certificate, the server's signature, the server's finish message, and the client's finish message. And then once we're done with the handshake phase, we move into the application data phase. So we take another string of null bytes, send it through the KDF along with the previous output, and we get an application data key used to encrypt the application data, along with this resumption key, which will be important for resumption. So, pretty easy. Okay, now resumption. So the idea here is we've already had a first session between the client and the server. How can we utilize that information? For instance, the client has already authenticated the server. We already have a shared secret. Can we use information from that first session to speed up the handshake in the second one? That's what resumption is trying to do. So it relies on some shared secret. And lo and behold, we have one. That resumption key that got spit out at the end along with the application data key, right? So the problem is the server needs to recall that resumption key. If, both parties need to know it if we're going to use it to bootstrap a handshake. So there's 2 ways you can do it. The server can keep a list of all resumption keys it's ever seen and give the client some identifier. So then when the client connects to the server, it sends its identifier. the server looks it up in its database, gets the resumption key, we bootstrap off of that. But of course, our servers are talking to how many clients? 100,000, a million? It's a lot of storage. So alternatively, we can offload that storage to the client. Now, keep in mind, this is going to be some shared piece of information. So the client knows this information. It can store it in its browser, it can store it in its operating system, wherever. For the sake of this, it has unlimited storage. The server is going to give that same piece of information to the client, who's then going to remind the server of that when we're starting a handshake. So it's a little confusing, but maybe this diagram will help. So this is our original TLS 1.3 handshake, kind of condensed. So when we're doing a resumption, we're first going to equip the server with a server key. This is going to be a symmetric key that's going to key AES or something like that. So right as we're finishing the handshake, now the server is going to send the encrypted resumption key to the client. And it's encrypted with that server key. The client doesn't know the server key, only the server does. And then we send application data. So this encrypted resumption key is a session ticket, and it's completely opaque to the client. But the client is going to use that to remind the server of what the resumption key is in the next session. Does that make sense? So to resume, we first need to have that session. The client needs to get that session ticket. So now, in our second session, the client can say hello and send the session ticket. The server is going to decrypt that and grab the resumption key. And now it can respond with its own hello and a purple finish message. Because it's encrypted, this finish message is encrypted with a key derived from the resumption key. And that's resumption. And look what we've done. Now the server doesn't have to send a certificate. It's not sending a signature. And the certificate takes up most of the bandwidth in the handshake. It's huge. And we can do this because we've already, the client has already authenticated the server in the first session. If the server can decrypt that session ticket and grab the resumption key and create a properly formed finish message, the client can be sure that this was the same server that it talked to in the first place. So let's dig into what's happening in the key schedule here. So our first session, we have those null bytes. We're not resuming. Send it to the KDF. We get our shared secret. Send it to the KDF. And we get the handshake key. Then we take the next string of null bytes, throw it in. We get our application data key. And we're getting the resumption key. So that was the normal session, the normal key schedule. Second session, we're resuming. So we're going to take the resumption key from the first one and have it bootstrap our second key schedule. Send it to the KDF. In this case, we have no shared secret. We're not doing Diffie-Hellman. So we just send it through twice. We get our handshaking key. This is what's encrypting the finished message from the server. And finally, we get new application data keys and a new resumption key to be used next time. Okay, this is cool. But in the first session, we had the shared secret contribution. In the second session, we don't. Well, what does that mean? That means that all of these keys used in the second session are only derived from the resumption key. Okay? And recall that the resumption key is sent to the server encrypted with the server's server key. What does this sound like? Sounds like RSA to me. Remember, in RSA, the server generates a key, encrypts it to the server's public key. We go from there. No forward secrecy. Here, it's kind of the same. It's only protected by the server's session ticket key, the server's server key. So if that is revealed to an attacker can then decrypt all these session tickets, get all the resumption keys, figure out the application data keys, we've lost forward secrecy. It's not ideal. So how do we fix that? Well, we say hello, we send the session ticket, and we also send a new Diffie-Hellman public key. We're doing Diffie-Hellman again. So here, the server can respond, hello, it's Diffie-Hellman public key, and a new finished message. This time, this finished message is encrypted with the key derived from the resumption key and the shared secret. So now, by introducing the shared secret, these next keys gain forward secrecy. Does that make sense? So in TLS 1.2, resumption looked exactly like this, but it did not do that second Diffie-Hellman step. It never did it. So they did not have forward secrecy. So kind of adding to our chart, by introducing only Diffie-Hellman and only elliptic curve Diffie-Hellman, we're basically always forward secure. In our previous versions, we weren't. We've gone from 2 round trips to 1 round trip, saving latency. And in TLS 1.2, resumption is not forward secure, but it is sometimes in 1.3 if you opt to do that additional Diffie-Hellman step. So some takeaways from this, if you are implementing or running a TLS 1.3 server. So always be negotiating those ephemeral keys when you're doing a resumption step. You want to have that forward secrecy. You can also rotate the server keys, the things that are encrypting the session tickets on an aggressive schedule. It's kind of a defense in-depth measure, and it will be important when we talk about zero round trip. So rotation kind of gives forward security, but of course it invalidates previous session tickets. Once the server forgets the previous key, session tickets encrypted with that key, won't be valid to it. So you have to go to the normal TLS 1.3 handshake. The other issue with this is if you have a server farm that a client can connect to any server and do whatever operations it needs to do. If you want the client to resume with any of those, they all have to have the same server key. So the question is, how do you distribute that? That's something that you have to think about how to do so securely. And of course, we're not really sure what the configuration and APIs and whatnot will look like, but don't assume that your TLS 1.3 implementation is secure out of the box. You have to make sure that you're, setting the negotiate ephemeral keys flags and whatnot. Question? These are different keys. So this is a key that it's a symmetric key only known to the server, only for its benefit. It's what's encrypting the session ticket. So if you rotate that, you won't be able to decrypt the previous session ticket encrypted with the previous key. So the only thing you lose is resumption. Okay, so now we're prepared to talk about zero round trip. So we need to be resuming a session. So we've already got our session ticket, and now we're being forward secure. So we say hello, send the session ticket, send our Diffie-Hellman public key, but then we immediately send early data, application data, right then and there. So this first bit is not encrypted, not enough information. The second bit is encrypted with a key derived from the resumption key. I will show the key schedule again, but remember, that was the first key to pop out of our key schedule. Now the server can say hello, provide its own Diffie-Hellman public key, a finished message, and the response to whatever early data the client sent. So that first bit is not encrypted, and the second bit is encrypted with the key derived from both the resumption key and this new shared secret. So let's look at that. In session 2, we start with the resumption key, send it to the KDF, and we get our zero round trip key, used to encrypt that early data. Then we get our shared secret, send it to the KDF, get our handshaking keys, we know this, KDF, get our application data keys, get our new resumption key. But what's the issue here? Well, when we were resuming, we added the shared secret to provide forward secrecy for these later keys. But the shared secret comes after the zero round trip key in the derivation. So the zero-round trip key is strictly and only derived from the resumption key. What do we say about the resumption key? If an attacker can figure out that server's key that's encrypting the session tickets, an attacker can decrypt the session tickets, get the resumption key. An attacker can then figure out the zero-round trip key and decrypt whatever data is there. So, kind of summing up forward secrecy in TLS 1.3, all of our non-resume sessions are always forward secure. We enforce that. Our resume sessions are only forward secure if we do that additional Diffie-Hellman step. And finally, our zero-round trip early data is not forward secure. So you got to think about that if you're going to be using zero-round trip, and ask yourselves, is this data particularly sensitive? You know, if it's just some GET request that's, you know, getting a user's profile, then that's maybe okay. There's no sensitive data in that GET request, presumably. But if you're making a post request with, you know, some PII data or something else that's sensitive, you got to ask yourself, like, do I want that to be forward secure? If so, maybe you should not send it as zero-round trip data. Does that make sense? Yes, question.
So there's something here that is also figurable, then you can disable the zero-round trip and you can change the and so forth.
Yeah, so are these results configurable? They should be. So I haven't seen any really ready-to-use implementations for, you know, the public, but I would presume that disabling zero-round trip would be easy. Adding in this additional Diffie-Hellman step should be easy. And I would assume, don't quote me on this, that it would be enabled by default. Now, does anybody see any other issues with the zero-round trip early data? Let's look at replay attacks. So in the normal zero-round trip case, client says hello, session ticket, Diffie-Hellman, early data. The server is going to process that early data. But an attacker can just replay that request, and the server will process it again. And they can replay the request, and the server will process that again. That's, you know, that's a big issue. So there's a couple things that we can do to protect against this. We can limit the session ticket time. So I said that the session ticket included the resumption key, but you can also include other things in there, like a ticket age. So if the current time is after this ticket age, we'll just invalidate it. The problem with that, though, of course, is an attacker could replay that whole request up until the ticket expires. Okay? One cool thing is, once we get a finish message from the client, we are convinced they actually know the keys. We're convinced that it's not a replay attack. So if we can buffer the request and then only process it after we get the finish message, we're still kind of harnessing zero-round trip data, and we're still kind of getting this speed improvement, but we're protected against this particular attack. So again, adding to our chart, we've introduced zero-round trip. That was a strict requirement for TLS 1.3, but there's no forward security on that early data. So kind of some takeaways about this. Kind of what I first said about the difference between a GET request and a POST request. If you're using zero-round trip, you should design those calls to be idempotent. You should not be performing any state-changing actions in these cases that an attacker could, replay and cause havoc with. Additionally, just don't turn it on if you don't want to utilize it. Don't turn it on for every single request. I mentioned buffering. You can set this max early data size that clients have to abide by, that you can buffer the request, wait for the finish message, and then proceed with the action. The specification calls out some actual replay protection techniques, but it's basically storing unbounded data on the server. So remember every single session ticket that you've sent. If you received it twice, the second one is being replayed, reject the request. Okay, so that was all about zero-round trip. We have a few other improvements. There's actually a lot to mention, but we've gotten rid of all export ciphers. We've gotten rid of all weak groups. No more logjam. No more freak attacks. We have only safe Diffie-Hellman and safe elliptic curve groups. We had compression before, which led to the breach attack. No compression allowed now. We had renegotiation before, which led to this cool, complicated three-shake attack and denial of services attacks. Now we have an easy key update mechanism. So that was a lot of information, but summing it up, TLS 1.3 reduces latency with its one round trip. It's a huge win for us. Resumption can be forward secure now if you enable that additional Diffie-Hellman step. Zero round trip data exists to further speed up processing of requests, but it's not forward secure. So you've got to keep this in mind when you are designing your application. And it's also prone to replay attacks, as we discussed. So, questions? I think there's a mic going around if we want to. There's no mic? Okay, yeah.
Hi, thanks for the great talk. Really appreciate it. You were talking about how you have to aggressively invalidate session keys to make sure everything works out nicely there, which is great. But it's I'm just hoping you can explain. It seems sort of offhand that if you do that though, and you start getting invalid session keys, all of a sudden what you were attempting to do is 0 round trips now aren't even 1 round trip. It's actually now 2 round trips again. Was I misreading the protocol there, or it seems like the consequences are pretty dire if you're invalidating those really aggressively?
Well, I guess it depends on how much you care about resumption in the first place. Because, I mean, you're right. If you attempt to resume a session and you've already invalidated the server key, so the session ticket is invalidate, you will have to fall back on the normal one round trip phase, which basically makes the handshake 2 round trips. Because you have the invalidation trip and then the new additional handshake. So you do lose in that way, yes. But keep in mind, by aggressively changing that session ticket encrypting key, you're kind of also protecting against these forward secrecy concerns against the 0 round trip data. Because once you remove that key from memory, it's gone forever. Anything encrypted with any of that 0 round trip data encrypted with that key can't be decrypted now. So
you'd mentioned earlier that it's supported on most devices. Where do you see from a ratification and adoption standpoint, from both a browser standpoint as well as a server standpoint, where do you see the biggest adoption and ratification of this across the bigger internet?
So I don't know if this will actually answer that specific question, but Cloudflare has an interesting blog about deploying TLS 1.3. And they found that I think now they get like 98.4% success rates, but there's a lot of middle boxes out there that don't abide by previous TLS specifications correctly. So it screws them up. So until they can figure that out, and they continue to modify what the handshake looks like to make it look like TLS 1.2. So these middleware boxes will be able to process it and basically then just reject it. But right now, fall back on our previous version. But right now, they just barf and they don't accept connections. So I think that's kind of the stopping point in widespread adoption right now. Hopefully that sort of answers your question.
That's what I basically heard from the community, is that it's kind of that intermediary third party, if you will.
Right. Yeah.
And it is the fallback. Everything's right now the fallback's not graceful.
Yes.
It's just throwing errors.
Right.
And then people bitch.
Right. Oh yeah.
So the question I was going to ask initially was around whether or not the server could simply encode its expected lifetime on the key to stop having to, so the client could read it and say, this key's only going to be valid until October or whatever, time in the future.
Right.
And then, so the client reads and says, I don't need to make that request because I already know this is going to be invalid. But I don't know if potentially that opens up some other problems.
Yeah, so there's a ticket time that's involved in that message. But I don't think that the specification even states anything about the client honoring that and not sending resumption requests after that. I don't think there's a mechanism for that, but that would be a good improvement. So suggest it to the working group.
Too shy for that, I think. But to his point, I think historically with these TLS modifications, we'll get server-side support, and it'll work, and it'll be out there for a couple of years, and then finally we'll start feeling confident enough that enough of the clients actually support it, right?
Right.
Before we'll actually get adoption on it,
So I think that
widespread anyway.
right.
We'll all be scared that, oh, we got a mobile app out there that's running on a, early version of Android that doesn't have any concept of this, and so it won't work. And then
Right.
potentially then we start looking at, okay, here comes the next round of downgrade attacks, right? Like because, I can force you back to TLS 1.2 and then attack whatever weakness was present in there.
Well, so that's an interesting point. I don't know if it really gets to that exact attack, but there's protections now in 1.3 that protect against downgrade attacks. So if a TLS 1.3 client talks to a TLS 1.3 server and an attacker attempts to downgrade them, the server, say we're downgrading to TLS 1.2 because we found a big break there. The server, the TLS 1.3 server, when it speaks TLS 1.2, will put a canary string in its random server value. So the client will be, because the client speaks 1.3, it will see that canary value and be like, hey, there was a downgrade attack. We should be able to speak TLS 1.3. Something's wrong. Abort the session. Yeah.
Great solid talk. So the question is about that use case that probably we all experienced in the past, which is a cipher is becoming insecure and you don't want people to resume, but you still want to, support it because, there's a bunch of clients there out there that support. How do you handle that?
I think you handle it by claiming and assuming that AES will be secure until we have quantum computers. And when we have that, we have AES 256 that we can fall back to. I mean, I think that I don't think there's any agility kind of mechanisms built into the specification, but it's one of those things where we'll add on to the spec to increase the cipher suite choices if that happens.
One of the things you mentioned is to reduce from 2 round trips to 1 round trip, it's going to guess which one it's going to use. What if they force it to guess the lower secure one? I don't know. I mean, is Diffie-Hellman and elliptical producing how much different security is there? But
so one, they have only included groups that meet a minimum bar. Okay, so that's one good thing. So it's the client who is. So an attacker will not be able. So the client guesses. If the server doesn't support that, or if you're attempting a downgrade, the server can say, "Hey, I don't support this. Try this one instead." So we fall back to the 2 round trip. But the transcript hashes between the client and the server will be different, so that will make the final key exchange fail because they will agree on different keys. So there is downgrade protection in that sense already built into the protocol.
Does the first question, does the spec have any recommended defaults for 0 round trip time? And the second question, is there any pieces of software clients that right now that won't be upgraded to support TLS 1.3?
I do not know the second question. The first, the specification is kind of vague, and it says, make sure you talk about the profile of your application. I don't know what the profile of your application means. The spec is very unclear with that. So they don't really, their guidance is, basically just don't turn it on unless you need it, or you know what you're doing with it. I think there was.
So you mentioned the 0 round trip was a requirement for 1.3, and it apparently has some implications to it if you use it. Were there any other requirements that were dropped because they weren't able to implement them in a secure way or successful way?
Not that I know of.
With 1.2, it was pretty transparent to the application what was going on with the cipher suite and how many round trips. With 1.3, you're talking about possibly conditionally disabling 0 round trips. So is that actually going to be exposed to the application in some way where I can talk to the server?
that's a good question. I don't know what those APIs and whatnot are going to look like. I'm gonna guess that the browsers like zero round trip, they know what they're doing. You know, for instance, Google. They know what requests to their backend servers are safe to use with zero round trip. So they will utilize that themselves to, you know, perform those actions, gain some speed. Whether it's going to be exposed and how it's going to be exposed to, you know, our applications, I don't know what that's going to look like. And I don't know. I don't want to make any.
So it might be in your application stack, you would have certain layers that wouldn't implement it because of whatever security implications, versus it just seems kind of crazy that, you know, you could have a Ruby on Rails or a PHP app say, oh, and by the way, Apache turn off zero round trip. Just, it's like
Yeah.
punching through a firewall that shouldn't feel permeable.
I agree. And yeah, I don't know what it's going to look like. So hopefully those you know, Ruby on Rails or PHP are able to expose that in a sane way.
Yeah.
Thank you. I have a question about what you see as the adoption of 1.3. I know that Chrome has implemented some of that, but what about web servers out there that you're aware of, mainstream ones that might already be adopting it?
I don't think that many. I know Cloudflare has. I think, yeah, I actually don't really know.
Thank you.
Is that all? Cool. Thank you for coming.